Hello and welcome to our lecture on the Rank-nullity Theorem. So let's jump right in to the material of today. So the first thing we want to prove is this following theorem 523. So we have two vector spaces V and W, and we have a linear transformation between them. Now, suppose we have a spanning set of V, then we claim that the image of T is actually spanned by the images of the spanning set. So in particular, if you start with something finite dimensional, so you have a finite spanning set, then the image is something finite dimensional. Okay, so we want to show this equality here. So as we've seen, in order to show the equality of two sets, we have to show that one is contained in the other. So let us start with the inclusion from left to right. And now let's go along our guidelines. Yeah, so this is precisely the reason why we talked about sets and how to prove set containment in the beginning, because we use it throughout, showing that vector spaces are the same. So we take an element on the left-hand side, and now the idea is, well, we want to show it in the right-hand side. And how can we do that? Well, we want to use the definition of the image. Yeah, so by definition of image of T, there is an element in the domain that gets mapped to this W. Okay. Now we want to use our assumptions. And what are the assumptions? Well, pretty much the only assumption is that we have a spanning set. And well, how can we use that something is a spanning set? Well, any element in that vector space is a linear combination of it. Let's do that. As V1 through Vn spans V, there are lambda 1 through lambda n in R such that V is equal to lambda 1 V1 plus lambda n Vn. So this is one of the things you might want to have as a reflex that, well, if one of your assumptions is that you have a spanning set, then at some point in your proof, well, you want to use that, meaning when an element appears from that vector space, most likely the next step is to use this and to write it as a linear combination in these. Okay. Well, and now what do I get? Well, let's look at our element W. I want to show that W is in the span of T of V1 through T of Vn. Well, this is, T of V by the choice of V. Now I can replace this by the equality above. And now the next step is, well, I'm going to use that T is linear. This is another reflex. If you see T of a linear combination inside your proof, if that pops up somewhere, probably what you want to use is that T is linear. T is a linear transformation, of course. And you want to break it up. Okay, and then you're already at the end here, because now you've written W as a linear combination in T of V1 through Vn, because this now is in the span by definition of T of V1 through T of Vn. So in this case, like kind of having these right reflexes kind of guides you through this proof. Okay, let's do the other inclusion. So let W be in the span of T of V1 through T of Vn. So what does that mean by definition? There are lambda 1 through lambda n in R such that, well, this W can actually be written as this linear combination here. Okay. Well, now you have the reverse reflex of what you've done here. Yeah. So if you see something like this, where it's broken up and you have that T is linear and you take a linear combination of these images, then most likely the next step is to actually pull it out. Okay, and now you've written W as T of something. And so this now by definition is in the image of T, yeah? So this might be, you might be a little bit blinded by this like really long expression here, but it doesn't really matter what's written in here. It could be a very complicated expression, but whatever is written in here should be an element of V, because otherwise this doesn't even make sense. And so then it's T of this, well, whatever expression it is. But in particular, since this guy here is in V, that means that, well, W is in the image of T. And this already gets us to the end of this proof. Great. Let's get to our next definition and then also to the rank-nullity theorem. So I'm going to put them up here together. So first of all, we're going to give the dimension of the kernel and the dimension of the image a name. So if we have a linear transformation like here from one vector space to another, and we suppose that the domain is finite dimensional. In this case, the codomain could potentially be infinite dimension. Well, so if the domain is finite dimensional, then we've just shown that the image has to be finite dimensional. So we let rank of T here be the dimension of this image, which is well defined. And well, the kernel is a subspace of the domain, so the kernel is also finite dimensional by a theorem above. And we call that the nullity of T. Yeah, so nullity of T is just another way of saying dimension of the kernel of T, and then rank of T is just another way of saying dimension of the image of T. And this only makes sense if the domain is finite dimensional. And now we have this following equation with the same input. We get that, well, the dimension of V kind of splits into the dimension of the image plus the dimension of the kernel. So the rank of T plus the nullity of T is equal to the dimension of V. So somewhat the idea is, well, if you start with your domain, it splits up into, well, if you take, there's a basis of the domain that splits up into parts of it being in the kernel. Okay, so this is, you're going to start with choosing a basis for the kernel. And then, well, now we want to complete this to a basis of V. And then this should correspond to, well, a basis of the image. So let's prove this. Let's give these names. So let M be the dimension of V and N be the nullity of T. So first note that this N is always smaller or equal than M because the kernel is a subspace of V. Okay, now we choose a basis for the kernel of T, say V1 through Vn. Great. Okay, so this is the part of the kernel here, the nullity that represents the nullity. And so now we complete it to a basis of V. So extend this tuple to a basis for V, say V1 through Vn, Vn plus 1, and then we know it has to be of length Vm, yeah, by dimension. Okay, and now we claim the following. So what we do here is, now we'll apply the linear transformation to these extra vectors in the basis. And then, well, we want that this corresponds to a basis of the image, yeah? And then, well, in this case, the equality above holds because we get N is going to be the size of the size of a basis for the kernel, meaning this is going to be, n is going to be the nullity. And then, well, this corresponds to the size of a basis of the image. And so if I add those two up, I get that they are equal to m, which is the size of a basis of the whole space. So claim is that T of Vn plus 1, T of Vm is a basis for the image. Well, we have to show that it's spanning and that it's linearly independent. So let's start with the spanning part. Okay, so we want to use the previous result. So since V1 through Vm spans V, the previous theorem, so theorem 523, ensures that, well, T of V1, and let me write it this way to break it down until Vn, T of Vn plus 1, all the way up to T of Vm, this spans the image of T. Well, but this now is equal to what? It's equal to 0, 0, T of Vn plus 1, T of Vm. Okay, so why are these equal to 0? Well, V1 through Vn is in the kernel of T. And the definition of the kernel is that, well, if I apply the transformation to it, they all go to 0. Well, so that means now that, well, the span of T of Vn plus 1 all the way up to T of Vm is actually equal to the span of, well, zeros. Yeah, that doesn't really do anything. This was one of the remarks when we were talking about spanning tuples. Well, and then this is the span of T of V1, T of Vm. And, well, we said that this tuple spans the image. So this means this is the image of T. So we get that this tuple here spans the image, which is precisely what we wanted to show. Okay. Then let's go to linearly independent, the second part of this theorem. How do we start a proof that something is linearly independent? I cannot say this often enough. We'll take scalars in R, lambda 1 through lambda n. In this case, sorry, I'm going to actually call this lambda n plus 1 through lambda m. Yeah? Such that, well, lambda n plus 1 t v n plus 1 all the way up to lambda m t of vm is equal to 0. So we take a linear combination in the tuple we're interested in and we set it equal to 0. Okay. Oh, and now the same reflex as in the first proof. Well, we have here something, a linear combination of things with t. So, well, what can I do? I can use linearity of t. By linearity of t, we obtain, well, what do we obtain? Well, we can pull this out. Great. Well, and then we at this point, well, now t of this expression is equal to 0. This means by definition, whatever is written inside has to be an element in the kernel. Oh, and pardon me, obviously this t should be gone. This is the correct thing. Okay, now we're almost done. Now we have to use that we already picked initially a basis for the kernel. Yeah? So if you find an element in the kernel, well, it can be written as a linear combination of any basis. As v1 through vn is a basis for the kernel of T, there are lambda 1 through lambda n in R such that, well, this element here is actually equal to this linear combination. Now we're almost done, which is equivalent to, and let's put everything on one side. So we get minus, oops, sorry for that, minus lambda 1 v1, and I'm going to write it as the following using results. So we're actually going to write here minus lambda 1 v1. So here you can see that I'm already getting a little faster with using these axioms, yeah? So, and I'm not even going to let you know what are these, but I think we can all agree that this is true. Okay. So we have this linear combination being equal to 0. But, well, what did we choose these v's to be? They were a basis. So in particular, v1 through vm, the whole thing, is linearly independent. So it tells us if we do find such a linear combination here being equal to 0 in v1 through vm, this can only happen if all the coefficients are 0. So as v1 through vm is linearly independent, we conclude that, well, all the coefficients are equal to 0. In particular, the last ones, because that are the ones we're interested in. Yeah, and so what was this? Well, this corresponded here, these here corresponded precisely to the one up here. So these were the ones we were interested in. So we showed that if you set up this linear combination equal to 0, you can conclude that all the coefficients are 0, and this is precisely the structure of a proof to show they're linearly independent. So this finished the claim, and then we're almost done. By the claim, we obtain that the rank of T is equal to, well, m minus n, which is equal to, well, the dimension of V minus the dimension of the kernel, so the nullity of T. And we can conclude. Okay. Great, so we have the rank nullity, and so using that we can prove this following result. Again, this is a very important one, and it will short track proofs to show that certain linear transformations are bijective. And this will be used as well a lot. Okay, so what do we have here? Let's take a linear transformation between two vector spaces V and W, and we assume that both of them are finite dimensional, and moreover they have the same dimension. So this is very important, yeah? If this is not true, then the theorem does not hold, yeah? And actually, it's not like does it not always hold, it never holds. Okay, and so what am I having now? Well, the main part is the following, that in this case, injectivity and surjectivity is the same. So this is the new result, yeah? if you see, you can actually block these equivalent conditions together. So we are claiming all of these 6 are equivalent, but like the first 3 are the usual equivalents of being injective, the things we already know. So injectivity is the same as the kernel being trivial. So we have this by a former result. That is actually theorem 47, which I said was very important. And then, well, this now number 3 is just a new reformulation. Well, the kernel is 0, then the dimension is 0. That's the nullity. And then the last 3 are equivalent definitions of being surjective. Well, either you're surjective, then lemma 448 says that surjectivity is the same as the dimension being everything. And then number 6 is just a reformulation of that. Well, if the image is equal to W, then that means the dimension of the image is equal to the dimension of W. And well, the rank of T is just the dimension of the image, and so the rank of T has to be equal to N. So the main part here is to show like some equivalence between the 2 blocks. Okay. So one thing I want to point out here too is, well, if you show that certain things are equivalent, in theory, you would have to show implication from each and every one of them to each and every other. Well, what you can do is often you can just kind of draw a picture of implications that will follow from other implications. So let me just write the proof strategy picture here. I hope this makes sense. I can definitely say more to this in the live lecture. We will prove the following. So we're going to prove that 1 is equivalent to 2. We're going to show that 2 is equivalent to 3. Or actually, let me put this in twice. So we're going to show that 2 implies 3, and we're going to show that 3 implies 2. Then we're going to show that 4 is equivalent to 5, because that we've already have. We're going to show that 5 implies 6 and 6 implies 5. And then the major part to connect, we're going to show that 3 and 6 are equivalent. Okay, so the point is now that starting anywhere, let's say we start like at here, we can go via the arrows everywhere else. So we can go from 1 to 2 via this arrow. We can go from 2 to 3 via this. We can go from this to here. And then we can go from here to here. And we can go to here to here. So this will show you that 1 implies all of these, by all these arrows. And so by this, we can often shortcuts proofs. So if we have like a long list of equivalent things, we don't have to prove every single implication. Yeah. And often, I mean, the least amount of work is usually to go in a circle, to go from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and then back to 1. Okay, and so let's start by this picture. We want to do 2 equivalent to 1. This is theorem 4.7. Now, 2 implies 3, so they're all going to be rather quick. The nullity of T, well, is the dimension of the kernel of T, which in this case, under the assumption that the kernel is 0, is the dimension of the 0 space, and then this will give you that it's 0. Now, 3 implies 2. 0 is the only space of dimension 0, so. Yeah, so if the nullity, if the dimension of the kernel is 0, the kernel has to be 0. Okay, so this was the first block, pretty much. Now we attack the second block. 4 equivalent to 5. Yeah, so surjectivity, the same as the image being everything. That was lemma 4.8. Now 5 implies 6. Is a simpler computation as above. So the rank of T is going to be equal to the dimension of the image of T. That by assumption 5 is equal to W, and that by choice of N is equal to N. Now 6 goes to 5. And so here you will see the first time the use of a subspace being of the same dimension, meaning that the subspace actually equal to the entire space. So we compute that the dimension of the image of T, so we assume 6, this is equal to the rank of T by definition. The rank of T is equal to n, so this is where here 6 comes into play. Yeah, this is equal to the dimension of W. Okay, well, great. Now, as the image of T is a subspace of W, this theorem, the number is 521, says that they have to be equal. Yeah, so subspaces of the same dimension have to be equal to the whole space. Okay, so this takes care of the second block. And now the most important part is how can we put these two together? So you want to show that 3 is the same as being 6. And this is where the rank nullity will help us. So I kind of want to keep those up there, sorry. So 6 says the rank is everything, and 3 says the nullity is 0. Okay, so by the rank nullity theorem, what do we have? We have that, well, the rank of T plus the nullity of T is equal to the dimension of V, which was being n. So now if rank of T is n, then, well, this here implies that the nullity is 0. So this is 6 implies 3. And now 3 implies 6 is, well, if now vice versa, the nullity is 0, well, then by the above equation, then we get that the rank is n. And this finishes the proof, and it basically finishes our lecture for today. But let me just say how powerful this is, yeah? So it's kind of funny if you think about it. You have a linear transformation between two vector spaces here, V and W. And actually what we are saying is that, well, if it's injective, it has to be forcibly also surjective, and vice versa. And now let's go back to, again, homework number 1, where I let you count injective and surjective maps and things like this. Okay? And this is, again, where the intuition of, for a finite set, the cardinality kind of corresponds to, well, the dimension of a finite dimensional vector space. What do I mean by that here? Well, let's see. Let's take a function from the set 1, 2, 3, 4, 5. So a set of 5 elements to 1, 2, 3, 4, 5. Well, in this case now, if f is injective, yeah, this also means that f is surjective. Because it means that every element on the left has to be mapped to a different one on the right. So I have like 5 elements in the image, so I have to hit everything. And the same if it's surjective, yeah, meaning I have to hit everything, then it also has to be injective because I only have 5 things to hit it with. Okay? And so then the same thing, if I have now here T from, let's say, R to the 5 to R to the 5, yeah, T linear, well then here T injective if and only if T surjective. Yeah, so if they have the same dimension, then, well, injective and surjectivity is the same. And so really the intuition and the reasonings, they're really similar to sets of finite cardinality in arbitrary functions. And somehow linearity is enough to be so robust for it to be true. That is all for today. Bye-bye.